An m by n matrix is a two-dimensional array of numbers with m rows and n columns. A 4 by 1 matrix, for example, has 4 rows and 1 column. And the matrix B that you see here is a 2 by 3 matrix, and it has 2 rows and 3 columns. Such matrices are notated as A, B, and C. And note that the matrix C depicts the subscript notation for identifying a single element within the matrix. Matrices with only a single row or column are sometimes referred to as row vectors or column vectors. Matrices with the same number of rows and columns are known as square matrices. In 3D graphics, 3 by 3 and 4 by 4 square matrices are used extensively. You can perform a number of basic arithmetic operations on matrices. As with vectors, addition and subtraction are performed component-wise. Thus, the two matrices must have the same number of rows and columns in order to perform addition or subtraction. Scalar multiplication is also performed component-wise, where the scalar is multiplied with each element of the matrix. However, matrix-to-matrix multiplication is a bit different. For matrix multiplication, a matrix with n columns can only be multiplied by a matrix with n rows. Each element in the resulting matrix is computed as the dot product between the rows in the first matrix and the corresponding columns in the second matrix. In equation form, if you consider each row of the matrix A as a row vector and each column of matrix B as a column vector, you can define the elements of the product C as follows here, with C sub I sub j is equal to the dot product of A sub I and B sub j. Here's an illustration of this process which might illuminate this topic a bit better. So each element of the matrix is made from the dot product from the corresponding row and column matrices. By way of example, consider the following matrices. Matrix A has 2 rows and 3 columns. It's a 2 by 3 matrix. And matrix B has 3 rows and 3 columns, a 3 by 3 matrix. The number of rows in B is equal to the number of columns in A. Therefore, multiplication is permitted. And the resulting product is a 2 by 3 matrix and is computed as follows. So look at the first component there. It's 1, 4, 8. So the vector 1, 4, 8 dotted with the vector 2, 4, negative 1. So it's the first row of the A matrix dotted with the first column of the B matrix. Matrix 1, 2 is made from the first row of the A matrix dotted with the second column of the B matrix. And 1, 3 is the first row of the A matrix dotted with the third column of the B matrix. So this yields 10, 41, 99 if we look at these dot products. So 1, 4, 8 dotted with 2, 4, negative 1 yields the value 10. So 2 times 1 plus 4 times 4, so that's 18 minus 8, 10. So the next is 41, 99, 7, 47, 105. Now, note that matrix multiplication is not commutative. The operands can't be reversed and yield the same value. And indeed, this is common. It's common that multiplication, which is defined for A times B, is not defined for B times A, as is the case for the 3 by 3 matrix multiplied by a 2 by 3 matrix. The transpose of a matrix is found by reflecting its elements over its main diagonal. For a square matrix, this is easy to envision, as demonstrated by the following example. So look at the A matrix, which just has the values 1 through 16 running along the columns. Now, if we want the transpose of A, we simply reflect those across the diagonal, and notice how the diagonal doesn't change. The values 1, 6, 11, and 16, which I've drawn a diagonal line through, are fixed. They haven't modified. But the values 5 and 2 have been flipped. The values 3 and 9 have been flipped. The values 4 and 13 have been flipped. The values 7 and 10 have been flipped, and so on. Another way to think of transposing a matrix is swapping the rows and columns. And this approach might be simpler to imagine, particularly for row vectors and column vectors, or for non-square matrices. For example, the matrix 1, 2, 3, 4, its transpose is the column vector 1, 2, 3, 4. And likewise for the column vector 5, 6, 7, 8, it transposes the row vector 5, 6, 7, and 8. Something to consider when dealing with matrices is how they're stored in a computer's memory. There are 2 possibilities, row major order and column major order. Row major orders are laid out one row after another. This is also the format of multidimensional arrays in the C programming language. The following example shows a 2 by 3 matrix stored contiguously in row major order. So notice how 1, 2, 3, 4, 5, 6 in row major order is stored contiguously. But conversely, the same matrix written in column major order would appear as 1, 4, the first column, 2, 5, 3, 6, the second and third columns. To convert a row major matrix to column major, or vice versa, is to simply transpose it. How a matrix is stored in memory can have performance implications, and various library methods depend on a particular order. Generally speaking, OpenGL uses column major matrices. The identity matrix is a special square matrix that has ones along the main diagonal and zeros everywhere else. For example, a 4x4 identity matrix is defined as you see on the screen. The identity matrix is essentially the number 1 with respect to matrix multiplication. That is to say, that multiplying a matrix by the identity matrix results in the original matrix. This concludes our introduction of matrices. In the next lesson, you'll learn about transformations and coordinate systems.